Well, it's great to see that so many people are still sticking around. This is the last talk of this awesome conference, and let's start by giving a round of applause to the organizers. Mulțumesc mult! Also, another round of applause. Chrome just turned 15 years, and like the speaker just before me said that he's a bit of old. I am too. Actually, the team was asking me, so what did you do when you were 15? And actually, I just gotten my computer, and I was playing around with Mosaic, one of the very first browsers, and I just installed this new browser called Netscape, and that really got me really excited about the web. So this is kind of like this is where my journey started, probably long before most of you. Since then, I moved on to Nokia, where I also worked on the web and browsers. So I have a small video. I worked on this phone here called the N9. This is the browser I worked on. It was really cool. But yeah, then we got a new CEO, and it became all about Windows Phone. And no one needed a browser guy like me, so yeah, I kind of had to move on. Very sad. So bye Nokia. So I moved on to this company called Intel. And yeah, this is me. I work at Intel as a principal engineer. I work on browsers such as Chrome and Edge. I also work on JavaScript and standards in the W3C. I've even been a member of the technical architecture group. So yeah, if you want to follow me on Twitter, or this thing that used to be called Twitter, now it's called X, you can do that right here. So the first thing you might be wondering is like, Intel, your semiconductor, why do you work on browsers? Well, the thing is that the world is kind of running on software, and if we do like some amazing new feature in our silicon, and there's no software for it, you can't use it. And as developers are moving to the web, well, we need to enable all those features on the web as well. So at Intel, we really value openness, choice, and trust. That's why we're working on both Windows and Chrome OS and Linux, and work in many different standard organizations out there. We also love sustainability, something very close to my heart, so just very happy about that. But you might be wondering, why do you really care about the web so much? Well, first of all, you have to understand if you're a developer or you're a small company, writing an app for iOS, one for Mac, one for Linux, one for Chrome OS, one for Windows, whatever's out there, you might not have the money for that. Or you might not even be able to find the skill set. So what we're seeing today is that a lot of companies are embracing web technology. They might be doing pure web, or they might be doing some hybrid approach, but they're definitely embracing web. So the vision we have at Intel is we see the web as a key application platform for creating apps. Not just websites, but we also want to focus on the strengths of the web, such as it has to run across different platforms, so it's about the cross-platform story, but it also has to load immediately. We don't want you to go to a website and then like, okay, I'm installing 5 gigabytes, just wait 10 minutes, no, wait another minute, no. It needs to be what makes the web work well. And it has to be safe, because that is the promise of the web. So how are we doing? We're actually doing quite well. We can make websites today that are installable, that have great UI. You have the single-page application. There are new specs coming out as view transition that allows you to make very nice transitions between views, around navigation, and it's becoming really fast and smooth. And that's something we really focus about at Intel. We really like performance. So, but what does a developer need? Well, you need a platform that has it's easy to use, it's easy to approach, and there's not all this kind of magic. So in many things we do, we don't bet on one framework and say that's what you're supposed to use. We're trying to make the web platform itself work in your favor. We also want APIs. We don't want APIs that are needed by every website out there. If you have a company that needs Bluetooth because you're interacting with maybe a Lego toy, well, that API should exist. You can't say, no, we're not doing Bluetooth because that's only used by 1% of all web pages or less than that. We really want that diverse set of APIs. And we want to be there for the next revolution that is happening in the web, revo.js, like for instance machine learning, or whatever comes next. Interoperability, of course, is also very, very essential. Like if you write a web app, it should work in as many different browsers as possible. Maybe not all the features will work in all, but then it should still not be broken. It should be like progressive enhanced. And I'm very happy that all the browsers have gone together and worked on this called the Interop project, both Chrome, Edge, Firefox, and Safari. And every year, people, like developers such as you choose the APIs you believe, you think should work interoperable across these browsers. And if you want to do that this year, you can scan this URL and you can submit your own proposals. So, how are we doing? Well, the web is doing really well. We have like 17.4 million JavaScript developers. And we know from our stats at Intel that around like 65, maybe 70% of time on our CPUs is spent on web. It's running web apps in browsers. But it's even more than that because you probably have some Electron apps that are also built with web technology. So maybe the real value is something around 80%. And these are our internal stats. As you can see, number one used application on Windows is Chrome. That's a browser. Second one is Edge. That's also a browser. Then you have Firefox. Oh, that's also a browser. Then you have Outlook. Well, Outlook is actually the new version is a web app. So also kind of web. Then you have other browsers, and you have Excel and Win and Word, and they're also becoming web apps. So it's really pretty much web. For these new APIs that I talked about, these diverse set of APIs, a couple of years ago, we all joined together, people from Microsoft, Google, Intel, Samsung, even Electron, and went together to create this called Project Fugu, where we look at what is missing on the web. We really want to fix those gaps and implement those APIs. But we also wanted to have like a cadence, a roadmap, so developers know that, okay, you fixed all the APIs I need today, but what about next year? And in 2 years, should I bet on the web, or will you leave me dry? Will it be so that, oh, there's no machine learning on the web, so I should have built a native app? No, we want to have this roadmap and constantly making sure that we are bringing the APIs that developers need to the web. And here are some examples of what we've accomplished. Visual Studio Code, like you talked that my friend Kenneth was here last time, and he was actually the PM on Visual Studio Code, and we had a discussion together. I asked him, why is this not a progressive web app? And he told me, well, we don't have file system API, that's really bad. We have that now. There's also some other things that was missing, and we also have that now, but we can talk about that offline. So now you can actually just go to vscode.dev and code in your web browser. It's pretty amazing. And like, come on, Photoshop web, like, this was the app, as I always said, like, that's the only thing we're never gonna get on the web because that's just too heavy. But here we go. You can open like 4 GB big images and it will work in your browser because they're implementing caching using a new API called the Origin Private File System API, super fast. They also use something called SIMD, Single Structured Multiple Data, that's supported by most chipsets today, that in some cases, in one case, it made 160 times speed up. But on average, it's something like 3 to 4 times. And all of this just enabled Photoshop to run in the web browser. Really, really amazing. And with all these new APIs, we also have like iRobot. They have this. They're using Bluetooth this is a small toy that kids can play around with, and they can learn coding in the browser. Really, really amazing. But what really is important here is that it's safe because it's the web. And we focus a lot on trying to figure out how to do that. Native app kind of have this, like, I would say, fake safety, that people believe that, oh, install this native app so it has been reviewed so it's safe. But they actually have access to all kinds of things on your system. We can't do that on the web because you visit a lot of different sites all the time. It really has to stay safe. So for instance, if you go to a website using Bluetooth, it's going to show you a list of devices around you. Those devices are not known to the website at all. Only the device you click on. And we constantly try to improve and come up with new ideas to make the web more and more safe. So our current focus at Intel is working on capabilities, making sure that, as we say at Intel, we want to leave no silicon behind, and performance. So some of the things I'm going to talk about today is that we're working on is WebAssembly. That's for running like existing porting like C and C++ code, Rust code to the web, even Kotlin now. And here we've been working on multi-threaded support and SIMD. We have been working together on WebGPU to bring modern GPU support to the web. Something really exciting is the Web Neural Network, or WebNN, for machine learning inference on the device, and compute pressure. So let's dive in and look at some of these things we've been working on. So one of the things with SIMD, this is a very technical thing. You can imagine that there's a computer instruction saying like, take a number plus another number. It's like one instruction. But there are actually some special instructions you can see here where you take a vector of numbers. So here 4 numbers and plus 4 numbers. And they will be plussed at the same time. And maybe you have even further hardware that could do it with 8 numbers or bigger numbers. This is supported in WebAssembly, but it's only supported for the 128-bit version. But here we just like manually, like automatically we identify the code and convert it to 265-bit. And with that, we in some cases see like a 1.5% speed up. So this is just one of the examples. We've also been working on web codec. So web codec is this API, like most hardware today, they have like media codecs in the hardware because you get a long battery life, just like decode, you don't want to do that in software. But you weren't able to use that on the web. So if you wanted to bring like Zoom or Google Meet to the web, they were like draining the battery and not using all that great hardware we had available. So with web codec, something we're working together with Google, that is now possible as well. And you probably know that from your phones. There's multiple different cores in your system, efficiency cores, performance cores, depending on what you want to do. And we also have that now. So we've been working on ways to identify and say like, okay, maybe this part of Chrome is not so important, run that at an efficiency core, run this other thing at performance because it's about UI interactions. And with this, we had like a 100% milliwatt power saving on Windows, for instance. Other examples, browse today are multi-threaded, so we try to minimize all those calls, and with this we got a 10% saving. That's just more battery life for you. WebGPU. WebGPU is something we've been very, very involved with. I don't think a lot of people know that, but Intel has actually been working on this for a long, long time, and this is finally shipping in Chrome, so really, really cool. But it's much more than graphics, because GPU, yeah, that's graphics, but with WebGPU, you can also use it for compute. So a lot of people are using this, for instance, for machine learning. So that is really, really cool, and we're enabling all that on the web today. TensorFlow, a very important machine learning framework from Google. There's a JavaScript version. Intel is actually the owner of the WebGPU backend. So we're seeing a lot of performance improvement just by moving from WebGL to WebGPU. Apparently there's one case that's a bit slower, but in general, everything looks good. Here's one example of us, if it's playing. It should be playing. Maybe it's not playing. It's supposed to be auto-playing. I don't know why this is not working today. Oh, there we go. So this is running in the web browser, and basically using like Stable Diffusion in the web browser. Machine learning is very difficult. There's many different kind of hardware, and people have this idea, well, there's one hardware is better than the other. That's actually not always the case. First of all, if you can look at this graph, you'll see that a discrete GPU, that's pretty fast, but it also has some startup cost because you need to move memory from the CPU to the GPU to make it fast. So that's really good for sustained ML, where you're running on the same data like a video all the time. But if you just need to do a simple task, sometimes even the CPU could be faster. So there's all kind of different hardware. There's a new category now called the Neural Processing Unit, NPU, or Google, they call it the Tensor Processing Unit. The industry hasn't really found the right term yet. So it would be great to use all of these things on the web. But machine learning doesn't necessarily have to be using these specific APIs. Sometimes it's a higher level thing, like using machine learning to do background blurring or identify where faces are in a video camera. So we're also working on these higher level APIs. So you as a developer would just use that. So, and that brings us to the Web Neural Network API. We are bringing machine learning inference to the web browser. And it's actually very, very exciting for my team. We're very proud of this. This is the first time on an official Intel roadmap slides we have seen a web API. Right there. Really, really cool. Very happy about that. And there's a lot of excitement building up. People from Microsoft and Analytic, whatever, are talking about this new web API that we're bringing. So you might be wondering, but why do we need native machine learning inference on the device? Well, first of all, like performance enables new use cases. The more performance you get, the more you can do. That enables you developers to build amazing experiences. But also, if we don't do it, well, it brings the web in a disadvantage compared to like native platforms. So we really need to do this on the web. Here's some of the examples of the performance. Let's zoom in a bit. And here's one example. This is standard, not doing anything. This is the speed. And then if I start using like SIMD, the single structured multiple data, you see a 3 times speed up. But compared to native, that's much faster. But with our new API, it's almost the same speed. So that really brings us on par with native. Really, really cool. So it's a new API that is created for AI accelerators. It can use both GPU, CPU, and NPU. And it will use the native underlying hardware if it's available. But it's also a very low-level API, so it's really meant for a platform like AI framework developers. So if you look at the option for ML on the web, we have WebAssembly, only runs on the CPU. WebGPU, obviously only GPU. But with WebNN, we can target all kinds of different hardware. As I said, the API is really low level, not something you have to work with. So normally, normal developers would use like a special framework for a specific thing like noise suppression, background blurring, or maybe go one level below and use something like TensorFlow.js. So let's look at this in action. So this is one of my colleagues out of China, and he's showing background blurring and video segmentation using both WebAssembly and WebNN.
Now I will showcase the background blur performance with the selfie segmentation model. It is a small model, and I will compare the WebAssembly performance with WebNN. Let me click the background blur button. You will see the inference time and the frames per second data showing the indicators. Furthermore, on the right side bar, I collect the performance data for every 2 seconds, display a total of 11 groups, and calculate the median value of them. Let me click the WebNN backend button. The inference time and the frames per second is faster, and the performance comparison result is based on the median value above. As you can see, the WebNN is about 2.5 times faster than WebAssembly. Now, I will showcase the background replacement performance with DeepLab model. It is a relevant bigger model than selfie segmentation, and I will compare the WebAssembly performance with WebNN. Let me go to the full screen and click the background replacement button and change the background at first. It's running on selfie segmentation now. Let me click the DeepLab button. By using the WebAssembly backend, you can see the inference time is more than 130 milliseconds, and the frames per second is about 7 in the indicators. Let me switch to the WebNN backend. The performance is much faster now. The inference time is less than 40 milliseconds, and the frames per second is more than 30. It's about 4 times faster than WebAssembly, based on the median value.
So yeah, as you can see that it makes a big difference being able to actually access that underlying hardware, especially as many CPUs and SoCs are coming with hardware accelerators in the coming years. Something else we've been working on is, or something I've personally been working on, is the Compute Pressure API. Basically an API to tell you how the system is experiencing pressure. This currently is for the CPU pressure, but it could scale to thermals, GPU, all kinds of other types of pressure, memory pressure, I/O pressure, and allowing developers to react to those data. So for instance, you might be having like a video chat and it's great, but actually the system can't keep up. So suddenly everything is slow, you're trying to share your screen, but the mouse is not even following. It's really a bad experience. In that case, as a developer, you might want to say, oh, maybe I should turn off some of the background effects or funny hats or just turn off some of the video streams. And this is what this API enables. It's very difficult though, because such signals are global state, and that brings it possible to actually abuse it, maybe sending data from one side to the other. I have actually proven that is possible, and we have mitigated it. So all of this makes it really, really challenging. Also, like we don't want people to be able to fingerprint users, etc., etc. The API is very, very simple. Basically, there are 4 states. Nominal, not much going on in the system. Very low load. Fair, something is going on. It's like doing quite fine. You get into serious, you're still doing fine, but you're getting close to the limits. And critical, you need to do something soon, otherwise the system might start like throttling and everything might become very slow and unresponsive. Here's an example of this demo. So here I made a small demo with an emoji that responds to the pressure in the system. And I have this Mandelbrot simulation that can be accelerated by using additional workers. And that really increases the pressure on the system. So you see, by adding workers, now it's in serious pressure. If I keep on adding, it should go to critical. And the same way, if I remove workers, it should go, or like stop it, it should quickly go back down. It's a very, very, very simple demo. So where are we? Well, this API is doing really great. We're working with there's a lot of interest. We have like Whereby is one of our users, but Slack and Zoom and others have also been using this API. And it has luckily passed all the different reviews that you need for standards. We've also been working a lot on median streaming. I guess median streaming is very, very important after the whole COVID thing. If you just look at the numbers, like Google Meet saw a 30 times increase in daily users after COVID. So a lot of people are working remotely now, a lot of people are doing meetings, online training. So media is really, really important. So we've been working together with these companies. You see Google Meet and Teams, they get 20% longer battery life now. YouTube is just as performance as the native apps, and Zoom got a 75% video encode latency reduction after moving to web codec. So we're also working on trying to identify what these companies need and what kind of APIs we need to implement. So for instance, with Zoom, you saw that for connectivity, we worked on web transport and WebRTC. For low latency, it's mostly like web codec, but also web audio. And battery life, there are optimizations in these existing APIs. But we also talked to them like, what APIs do people need? We already talked about web codecs for like hardware acceleration codecs, but people really want these high-level APIs for background blurring, just use the hardware that's available, phase framing, noise suppression. It should just work out of the box. So not every developer have to go and implement that themselves. So here's some examples from my co-workers showing how this is now working with their prototypes. I think this is actually shipping in Chrome. So this is background blurring. See, that works pretty well. I think someone else is joining. I don't know if. Let's move to the other one. And we want to keep these APIs very, very simple. So basically like a 1-line, 2-line opt-in, and you will get all this feature for free. Looking at what we get out of using hardware, here's the example. There's no background blurring. It gets like the power is like 100% or 1 here. With our proposal, it's just a little bit more. If you were to use something like TensorFlow.js, you see it's 2.5 times the power usage. That means less time using your devices. Face detection we worked on for a long time. We started to use with OpenCV back in the days. It was using WebAssembly, but it was 8 megabyte, a bit too big. Google, they did the same. They managed to make it to 2 megabytes with a media pipe. But now we're working with WebRTC to actually building this straight into the standard. So here's an example of that. So it's following the user pretty well, and even if you have multiple users, it should also work fine. There you go. Pretty nice, very, very simple API. And as you see here, we're just doing face detection mode bounding box. We are working on making this a bit more advanced so you can get the whole contour. So if you want to do like funny hats and effects, like you know from Snapchat, that should also be possible. And just like before, our proposal just used a little bit more power. If you were to use like one of the machine learning APIs, it will use much more. We've also been working on all these APIs called zoom, pan, tilt, zoom. A lot of cameras support that. But now we are doing that also automatically. Why not just follow people around? As of maybe a one-line change. So this is our prototype, works pretty well. This is something else we're considering doing. That is actually you probably know that in meetings, you never look at the camera because it's on top of you. And it looks kind of weird because everyone is looking away. But with machine learning, you could just modify their eyes. And yeah, maybe we'll do this, maybe we won't. We'll see what people think. Also, like we had all these, a couple of years ago, we had all these APIs to change exposure time, brightness, but like, it's very difficult for users. Let's just do it for you. Automatically, line correction, on. Use machine learning, whatever is available. So that's basically all I had, but before I'm ending, I just want to show that Intel is also working on all kinds of other cool things. So I actually got this video just like an hour ago from my coworker, Alexis. So he's been working on supporting foldable displays. And actually, I worked on that as well a year ago. So he's been doing the implementation. I worked on the standards for it.
Hi everyone, my name is Alexis Menard, and I'm here to tell you a little bit more about the work that we've been doing to improve the foldable devices on the web. So here's a little example. I have this gallery demo where you can scroll through your pictures, and then if you select one, then it opens it full screen, trying to use the available screen states to show you the picture as the biggest as possible. That was great. However, when I undock the keyboard on the foldable device, I have this extra screen state that comes down. But then, because the gallery hasn't been adapted for them, then you can see that it tries to lay out the picture in the middle of the fold, which is not really a great user experience, especially if I use, for example, a portrait picture that looks very odd. Now, I have the same demo, but with the APIs turned on, and for foldables, we have adding two new APIs. So the device posture API, which allows you to get the overall posture of the device, how the device being used, as well as the viewport segment, which tells you information about the top section, the fold section, and the bottom section. So for that same demo, if I, for example, select the picture, you can see that now we lay out the picture on the top section of the screen, which is a lot better. Here's another one in portrait, which is what the user would expect. Now we went a little bit further on this demo, and then when we use the device in book mode, then we provide actually a split UX. And you can see here, I can select the picture, and then it shows on the right with extra information, right? So that's a playful way to improve the user experience. And I have another demo that actually embraces the form factor. So I don't know if you're probably familiar with this little demo, which is the fold ship demo. It's like the battleship when we were young, where you have your enemy fleet and you have to try to find them, and then you have your own fleet. So in this case, I'm a bit limited in terms of screen state to display extra information. I have to basically display the most important part of the game. Now, with a foldable, I have a lot more screen state to play with, and I can do something like this, where I put the bottom section as your own fleet, and then the top section as your enemy fleet, just like the actual real physical game. And I use the fold section as a playful area to display extra information. Another demo that actually leverages the form factor is this one. So this would be a typical news website, right? You scroll down with articles and pictures. Now, if you rotate the device and read in book mode, then you can see that I've created a paper quiz imitating a journal. And then if I put the device in flat mode, and then it changed the layout, and then if I deploy the kickstand, then I can have like the actual normal screen layout, right, with no fold. And then if I fold the device again, then the paper quiz will appear again, right? Thank you for watching, and you will find more details in the link provided in the presentation.
So yeah, as you've seen at Intel, we're working on a lot of new APIs and really trying to make the web capable and fast so that you can build your experiences using just web technology. And with that said, I want to say thank you very much for having me here today. and I hope I'll see you all at the after party.